Hi, I'm Brian Martin, and I'm going to be talking to you today about some of the problems and solutions and fun that we've had building the data network for the ATLAS experiment at the Large Hadron Collider at CERN in Geneva. And the team is rather hoping that some of our experiences and solutions will be of interest to you guys in the real world here. The ATLAS experiment itself is very, very large. If you look across at the I can't see whether, because these small white dots here, these are the hard hats of people working on the thing. For people over there, it's over there, okay? So it's very, very big, and it produces lots and lots of data, and it weighs a great deal. And the picture on the top right shows you the kind of reconstructed image that the detector produces once the data has all been sent out and reconstructed in the data farms that we're looking after. The total output of this beast is about 80 terabytes per second, which is quite a lot, actually. And they use hardware triggers to reduce it down to something slightly more usable, which is what we start to see at the Ethernet level, where it arrives at 160 gigabytes per second. We look basically at partial events, so that 5 gigabytes per second of this goes to about 200 processors. And then we give the thumbs up or down as to whether or not they're interesting, and the next level will then fetch the entire event to come down, and there we send it out to about 2,000 processors, and again we give the thumbs up or thumbs down, and we cut it down to a manageable 400 megabytes a second, which goes out. The magic number about that is it's about the limit that you can actually record onto disk before sending it out on the grid to the rest of the world. Any more than that, then there's just not enough computers left in the world to do the analysis. Because don't forget, there's not just us. There's 4 other experiments doing the same thing in real time. Around the data flow part, we put the control structure, and around that, eventually, when the build-out is finished, we'll put our monitoring. At the moment, we run it over the control structure, but when things start to get really busy, then we'll migrate outwards. So we're looking after a total of about 8,500 ports in this system. We also have a small problem. We have demanding customers, just like you guys do. The network was dimensioned to meet so-called requirements, so we cunningly built it larger than we were asked for, so that we would have a maximum average link occupancy of less than 60%, which meant that, at least in the plan, that we would go home and sleep peacefully at night. Unfortunately, this is actually seen as a challenge by the physicists, because to them, 60% occupancy means they got 40% for free, and so what they will normally do is just turn up the wick until you saturate something, something breaks, and then they back off just slightly. So you're running permanently at maximum demand. So now we can't distinguish anymore between what are real problems because we're oversubscribed somewhere, or rather undersubscribed somewhere, and the self-inflicted injuries. And we need to be able to do this to protect ourselves and also to help the community get the best out of the system. And the only way we can accomplish that is basically by monitoring everything. So what is out there? Well, we did the easy thing. We looked around what was being used in the computer center, who used Computer Associate Spectrum. They've used it for 10, 20 years now. They're quite happy with it. And it really is good for tracking component failures. We discovered very quickly, however, that it's a very good system. It takes all of the data, it stores it very, very well, and then hides it from you. The trouble there is that even at fairly low polling intervals of about 5 minutes, the report gateway is already a problem. If we have a drop for any time, we have to wait for the system to catch up just to find out what's been going on. And we discovered to our cost that there's no support at all if we want to poll at less than 5-minute intervals. And we were thinking more like a few seconds. And in fact, we made a compromise and we said, okay, we'll do this at 30-second intervals. And the problem there was we almost immediately ran into a block because we discovered that we were getting polling drops. As you can see in the graph at the bottom, the system would just sort of give up and go out to lunch. CA did what they could, but basically they said, you know, when you're running at that speed, you're on your own. But from our point of view, we couldn't accept 5 minutes because this is being used in a feedback loop. Nobody's going to change a parameter and then wait 5 minutes to see what the hell's going on. Okay, so we said, no, we have to have the speed. And in order to find out what the problem was, we essentially ended up writing our own polling engine so that we sort of were second-guessing what Spectrum was doing in order to find out what the root of the problem was. And we did, in fact, find it. But by that time, we had a wonderful polling engine, which is fast and it's reliable, it works, there's no drops. And the good thing for us, our point of view, is that it takes all of the data and it stores it both in an in-RAND database and into disk RRD files, so that all the data we want right here and right now is in memory, which makes the visualization really easy. And we solved the bug. It was an interesting one. It may amuse you. One of the earlier speakers talked about some of the first-grade software in the edge switches. He's absolutely right. What happened is, in this instance, was that SNMP requests to the switches were being responded to in some particular cases by delays. And these delays were coming from switches which had trunks enabled in the switches. And the delays, whether they were being used or not, didn't really matter. And the delays could be anything from 1 up to 5 seconds. Now, a 5-second delay to an SNMP response, as far as Spectrum concerned, was a bit like Mogadon. It went to sleep and it would wake up some time in the future whenever it felt like it. And they never did find out what that was, but at least HP fixed their problem. Given the fact that we were overrunning, therefore, what the Spectrum support, we had to reconsider our options. Sorry, going the wrong way. We decided we put Spectrum one side, we'll keep it for what it's good at, which is failure alarms. We looked at Cacti. It's good for visualizing single plot RRD data. It says here no plot aggregation. You can actually get in a plugin which will do multiple overlays of plots, but it can't handle non-RRDs, and it can't handle S-flow time series. And we can't use it with external discovery, so we gave that up. Buried inside Cacti, in fact, is Spine, which is a very stable and fast polar. And if we'd known that then, we would probably have used this for our own poll engine and added our own Go Faster goodies onto it. It's a very good product. But for to meet the monitoring everything, we also need to know about the host CPU stats. So sysadmins had decided a long time ago they were going to use Nagios. They looked at Lemon. It was fairly, it wasn't really very flexible, so Nagios was their choice. Unfortunately, it has poor plot visualization, at least the instance of it that we have at CERN does. Pulling plots out of Nagios is a bit like watching paint dry. We also wanted S-flow collectors. You can buy an S-flow collector. They're not cheap. But the problem is they don't do proper data archiving, and we wanted archiving for post-mortem analysis. And we thought we'd also need something for environmental stats, because there's no point getting excited about a bunch of switches dying if it turned out that some clown has turned the power off. And therefore we needed to know the environment stats for that. And so you see here already we have a large selection of data sources for monitoring, and how do we pull it all together? Well, what I want is one-stop shopping, because what I don't want is multiple interfaces to have to learn and train people how to use. So how do the pros do it? Well, this is the Spectrum visualization here, and at the top left you've got the auto discovery, which is a bit of a pain because it changes every time something comes in or drops out. You can, in fact, we wanted to be able to represent to our users the architectures that they're familiar with, the way it's laid out. And you can, in fact, as you can see on the bottom left, force different components to occupy space that makes some kind of visual sense to them. And this works. The problem is that if you actually do an edit of any of these components, the whole thing collapses and you get the pictures on the top right. If you add to that the fact that you can't overlay traffic onto the links, basically it's really not doing what we want, and we had to look elsewhere. We pretty soon came upon a system called Guess, which is also open source, and this has the big advantage is you can overlay the traffic volume as a color code onto the links. And in the bottom left picture there, you'll see the second value added we did, because equipment will always be arriving and departing depending on its state of health, but we always wanted to be able to show the entire system looking like our architecture. So all of the various classes of devices, the edge switches or the core routers, or out on the left, the control structures, we offer each of these instances an origin and a vector for displacement, so that no matter what is alive or not alive, all of the remaining equipment finds the right place in the firmament, and we can actually see the entire picture. But only of switches, no hosts here, because if we put the hosts in as well, the whole thing just gets far too busy. And this is what it looks like as you, every 30 seconds it updates, and you get a very clear picture of where all the traffic is, and you can instantly see as things are going on if you're happy with what's happening or not. And we already exported that out to the users so that people on shift could have a good idea that their world might be collapsing around their ears, but at least the network was perfectly happy. And so we came to the architecture of the final system, where at the bottom you see our SNMP polling engine. We have a set of databases which are central, and all of our other systems feed into these databases, and on the top we have the various visualization packages which feed off of the databases. And so we looked forward to a nice, quiet, easy time while we developed this, ready for when the machine was going to be ready. But of course, you know there's an advanced clue there. Nobody has a nice, quiet time. We had a very serious wake-up call. We had a power failure in the cooling system, but we didn't have a power failure in the computer room. So what happened is things got very hot very quickly. In the infrastructure room that we have, temperatures were rising about 1 degree centigrade per minute. And so the idea is when you have a problem like that is you have a tested fail-safe plan. And clearly we didn't. We dropped the ball on that when everybody thought somebody else had done it. And in fact, the monitoring worked perfectly. It's getting hot. It's getting real hot. It's awfully hot in here, guys. And nobody noticed for about an hour. The post-mortem was interesting. And it's a word of warning to you guys as well. The very first thing to fail was the fiber links. They go at about 40 to 45 degrees ambient. And therefore, if you've got yourself mission-critical links, you better have a copper backup someplace. Nobody actually expected that we would actually hit this kind of problem, because Intel's got all this nice thermal management problem. And if things get hot, then it skips cycles and eventually will stop working altogether. And that's true if the motherboard that they're living on allows it to. And our vendor had suppressed all that. So these would run at 100% until they went down in flames. We've also got fan controls which are supposed to speed up and increase the cooling as things get warm. And they would have if sysadmins hadn't discovered earlier that if you run the fans at full speed, the vibration on the motherboard causes the head bounce on the disk, which means that latency goes up and you can't use it as a file server. So they cut the speed really down so that the latency would be fine. Routers, they've got a nice system for load shedding when things get hot. It never worked because the power supplies and the fans went long before that kicked in. Beware of UPS. If you have UPS in your room, then you also need an uninterruptible cooling supply. We didn't have one. And the last word just about SMSs. We had a complicated system of SMSs. Put not your trust in this. One guy was asleep. The other guy, his inbox was full. My machine was charging in the kitchen. And in any case, it didn't matter because the messages were too long for the buffer and you couldn't read the magic numbers that you needed to know. We dodged a bullet on that one because things did come back to life. I need a drink here. And what you see here is the opening panel of our network browser, which gives us an overall system summary. This is the first time I'm seeing what I really want. Excuse me. Because here we have the architecture laid out, and I can see at a glance all the various profiles are all looking roughly the same, except the one at the bottom, which is burst transmission out to the system. Everything is fine, and for the first time I have an overall picture of what is going on. But I go back again, sorry. But again, this is just the core. I don't see hosts. What do we want when we're looking at a host? Well, every tool will produce a single plot. It's usually auto-scaled, and we're interested in that, of course. But we also want to see the load as a percentage of capacity because, as I said, we're running at capacity quite often, and we're also interested in the discards to see how hard TCP is working, and we'd love to see any of them overlaid together so we can collect a set of peers and see if they are all pulling the weight correctly. And so we do this, and we've integrated this into our work panel, and I'd like to spend a few minutes just looking through this system here with you. I'm going to work on the slide over here, so you have to those on the left are going to have a problem here. Here we have our aggregated overlay, which shows all of the instances of the particular peer group that we chose from the menu here. And in the sub-menus here, we see mini plots, which will display any of the parameters that we want. Typically, we would put load here, errors there, and the auto-scaled version, so we see something, if anything, which is going on. The display itself is based on the time slot that we see here. We've chosen the most useful peer groups here, but if we wanted to cut things down and filter it even more, then we can put in a regular expression in here. And this is the root look and feel of our system. And in this particular case, we're pulling up the traffic polling system. But the magic window is this one up here, which tells us which database are we looking at. So we can now change that and say, okay, we're now going to pull up the S-flow statistics. And so we have this exactly the same look and feel. And the S-flow, of course, is going to tell us not just a question of how much traffic there is, but who's doing what to who and why, which will help us with debugging. And by, again, changing, this time we're looking at the statistics for the CPU system. And in the mini plots here, we can pull out any of the usual CPU run temperatures, system temperatures, the CPU load, the memory usage, anything we want to know about the host CPUs, and we can do that for any of the class of the processors that we see there, and it's the same look and feel. And then we can also then pull in the environmental stats. And again, it's the same here. We're looking at you can see this. It's the average temperatures in the racks that are being looked at. And you can also see the water temperatures and the power or the fan status temperatures as well. We also have dynamic pages with real-time traffic. Everyone does those. I'm not going to discuss it for too much. Now, the guest display that I told you about earlier is good for seeing switch-to-switch traffic, and as I explained, we can't incorporate the host details. The browser, which I've just walked through, will give you all the host details, but you have to dig for them. You have to know what you're looking for, and you have to be pretty much of an expert to understand what it is that you're seeing, even then. But I want to see all of the detail when something goes wrong, because what we're dealing here with is a process. It's a bit like a factory automation system. If we have garbage out at the bottom, I don't want to spend my time on that because the odds are that it's come from garbage in at the top. So I want to focus on where the real problem is, and for that I need to correlate things that are going on across the entire system. And when it is going wrong, I want to see the neighbors to see if it's an isolated case or if there's a whole class of devices that are in a problem. And when I look at this, I want to see a different view and a different level of detail depending on my viewpoint, the level of abstraction that I'm comfortable with. And I want to be able to fly through it because there's a lot of stuff out there, and I want navigation and visible errors. It's all about me, isn't it? It's what I want, right? Because what I really want is Google Earth in my network, right? We actually tried it. I built a network the size of Greenland, but it wasn't very practical because the coordinate system is based on geography and it's not based on logic. So. And in those days, either you couldn't do dynamic update requirements. So we went looking for some display software that would do this. And the vehicle of choice is X3D, which is an enhanced VRML. It comes with a freebie viewer, and it's free for a reason. It's not very good at all. And we went looking for something that would handle up to 1 million simultaneous instances, and we found it in Octago Player. And this is the view that now we have constructed. So the green circle in the background is our control plane. And brought to the foreground is the furniture, which are the main architectural structures. It's the farms of processors in the square boxes, and it's the core switches in the round boxes. And draped onto the furniture are graphs of what is going on at the various levels. And at this top level, what you're seeing is aggregates of all of the traffic that's going from one of these building blocks to another. If I was to zoom in at for example, the center core here, you're starting to see windows here which are essentially the receive and the transmit traffic. In this one, there's receiving nothing, the transmission is receiving a lot. And underneath there is bars of whether or not we're in a state of happiness or there's something wrong and we ought to worry about it. And if I zoom in even closer, then you have this nice little icon here, which is the graphing icon, and this will pull up any of the statistics about the structure that I want to look at. So I can pull out of the system any of the particular ports, I can pull out all of the stats that you've seen before, whether it's environmental, traffic, or whatever. It's all there, and I can look at it in detail. If we fly into one of the big compute rooms, this top level picture here is the distance view, and we have an amphitheater of racks of equipment, and I can see instantly, the moment I walk in or fly into this room, that there's 1 or 2 or 3 racks which are showing some high level of activity. This isn't a simulation, by the way. This was done during Saturday night's run, and it was emailed to me while I was here. And I can see that there's some areas here which are a little bit congested, so I can fly in, and this then gives me the second picture here, and now you're seeing the detail on all the individual processors as I'm beginning to see the windows there, and at the bottom I've flown right in and I can look at one specific processor and say, well, are you having a nice day or not? Yeah? So in conclusion, I would like to show you the video of how this works. If only I could get the thing to work for us. Let's have a look. I may need to resize this. No, I may need to kill it. While I'm playing, you can think about questions. Okay, so this is a screen capture that was done over the weekend's run as well. Just a couple of seconds there to see the view. So you've just flown in to look at the core. Everything is fine there. You're noticing up at the top here, there's some slight congestion there. It's yellow, it's not red. Here we have some congestion in the XPU farms. The rest of the system seems fine. So let's go and have a look up in here. So we fly into this area there. And immediately you can see that this is the guy that's got the problem. So you fly into him, and it's one of the sub-detectors which is putting out a little bit more data than we would think of. So we pull up the plots and we look, okay, it's nothing terrible. We can ask the guys why they're putting out more than they normally did, but you know, it's not fatal. Data taking will go on perfectly happy like this. Let's go and see what the repercussions of that are. So we fly out of this room. Here we have these icons there. We discovered when navigating in 3D, it's very easy to get yourself lost. So, so we needed a quick way home to something that we recognized. And this is flying into the XPU farm, the third level processing farm. Here's the area that we're flying into. And then you see how the detail is increasing as we're getting in towards it. And then we see that essentially everything is fine because this is the receive of the top of rack switch, and it's completely and utterly saturated, which means we can't do any better than we're doing at the moment, which is fine. So everybody's happy. TCP is working its guts out, keeping up with it, but we cannot do any more than we're doing, and so it's not really a problem at all. Thank you very much.
Thanks, Brian. We have time for questions. Please do announce yourselves so we know who you are.
So, Tim Brown, Cisco Systems. Just two really quick questions for you. The first question is, on the system side, it seems like you're doing a lot of polling as opposed to messaging. Was there a reason for that decision, or are you in fact doing more messaging-based back to your...
It's polling. It's all SNMP polling throughout.
And what was your rationale behind going that approach versus trying to message the data? Because it seems like in more large-scale implementations that I tend to see or look at, I see a lot of people kind of shifting to a messaging-based approach where the hosts themselves or the elements themselves kind of message their data.
In one of the other experiments, they did this because they have tighter control over the applications. They've instrumented the transport layer software, and they've gone that route. We are slightly more of a individualistic, shall I say, experiment. We are dealing with physicists here, not company men.
Sure.
So there was no possibility whatsoever to instrument the application level. They were desperately trying to get the thing to work just to be ready on time, let alone do subtle things like this. And so we were put into a defensive situation, and therefore we polled everything.
Okay.
And in fact, it's very, very useful because doing this system, we spot anomalous things that the application guys aren't aware of. For example, we see linear growth in traffic. The application guy is completely unaware of it because he has a bug in his system. He's reporting back statistics to somebody, and instead of overwriting his record file, he's appending to it, which is fine. You know, for him, everything is fine. The network will eventually fall over, however.
Right. The second question, I was looking at your list of tools that you investigated earlier in the deck, and one tool I didn't see on there, and it didn't surprise me, but I was kind of surprised that it hasn't received more attention from the operational community, is a tool called Graphite, which I believe portions of it were talked about at Google recently. I'm not sure what they're using it for or if they're using it, but did you look at Graphite at all? Or?
No, we didn't.
Okay. It seemed to solve a lot of problems in kind of the traditional RRD-based approach.
The bottom line was we were up against a rock and a hard place. This business with Spectrum took a year to get to the bottom of it.
Right.
We tried every known combination, and eventually we just ran out of time and said, look, we really have to deliver something.
Yeah, and I don't think Graphite had even gotten any press except for like the past month or so.
Okay, well, this was all being put together, started about 2 years ago, and the data came online about a year ago for the first time reasonably heavily. So we didn't have a lot of luxury to go and tour the market.
Great, thanks very much.
Okay,
Good
you're
presentation.
welcome.
Morning, Wes Hardiker, Sparta. I'm a big fan of visualization. I'm a big fan of graphs. The one thing that I've had a hard time with over the years is that I keep falling in and out of actually using it. And I think that comes mostly from an operational kind of sense where you can spend all of your time playing around and zooming in and out of things, and then you spend all of your time doing that and you get nothing else done. And then I fall back into working in the real world and looking at all the nitty-gritty all the time, and I forget about my visualization tools. And so some of my question, I think, is, A, how long has this been in production, and how much have you used it? And can you give me a real-world feedback for as how much of your daytime, in fact, you spend looking at this versus looking at other data? It's a really cool system. I'm very impressed.
Okay, well, there's a number of aspects to this, and I sympathize and agree with a number of your points. The workhorse is the multi-windowed browser, and that there's one main user of that, and it's me, and it sucks up about 2 hours of my life every morning. Okay, and it's not meant for the long haul in the sense that I intend to do this for the rest of my life. The database structure that we have is a platform onto which we will put an expert system which will then dig into there and pull the interesting stuff out and warn us. But to have an expert system, you first need an expert. So I need the visualization tool so that you can be comfortable with knowing what the system really looks like as it is operating what they call normally, which is in fact it goes through an order of magnitude every few minutes as things evolve. As for the 3D, it's purely in the prototype stage at the moment, and that is looking forward to the moment when the developing team has all gone on to better things, and we're left with non-experts looking at the system. Now, the guys coming up who will be doing this in the future, they've all grown up with their iPods and their 3D games, and they're not going to sit down in front of a menu-driven, menu drop-down system that requires them to be expert in everything. If it's not made simple and easy and intuitive, they're not going to touch it and they won't be able to use it. So this is looking forward, or rather preparing for that day.
Yeah, I agree. You have to train for the 18-year-olds. The problem is that after you've shown them visualization, you have to teach them what to do next. And the other thing that I run into all the time is I often look at the same graphs and say, yep, that's still red. It was red yesterday. We need to add more fiber, and it'll be red for a long time from now. But it's a very cool system. Thank you.
Thank you.
We have time for one more question.
Hi, Babak Pasdar, Bat Blue. Okay. I wanted to understand how you went about setting up baselines for all the metrics that you're monitoring, tied, application tied to network usage, tied to CPU, you know, all of those types of things. How did you go about getting all the different resources within the organizations that are using those applications and systems to give you the kind of data that would identify the baselines?
Because it's all in one experimental team. All of the data that goes, all of the monitoring data is all goes to one control room, and nobody's hiding it from anybody else. The main issue is digging through it fast enough to understand what is or is not going correctly. So we don't have any, there's no firewalls between the data. Each of these tools goes to the expert group of question. So the environmental guys, they use their PVSS and they have their own look and feel and interface to it. We just plug into their database and bring it into our visualization system so that we can correlate with all of the other data that's flowing at the same time. And this makes it a good selling point because of the one-stop shopping, if you like. So we don't have a problem. There's no boundaries between the data as far as the rest of the suppliers are concerned, which is not the case for you guys, clearly.
Thanks, Brian.
Thank you.